Welcome to rigorous training in longitudinal data science. Radiance.
Good day, everyone. My name is Andrea Aparicio. I am an associate lecturer in statistics at the Great Ormond Street Institute of Child Health of the University College of London. Today, we are diving into an important part of statistical analysis within health research, sensitivity analysis. By the end of the lecture, you will be able to understand the fundamentals of sensitivity analysis. You will also be able to recognize different dimensions and types of sensitivity analysis, and to identify the limitations and challenges inherent in sensitivity analysis across different case studies. Let's unpack what sensitivity analysis means and why it is so important within health research. First, let's define what sensitivity analysis is. In simple terms, it's a method to determine the robustness of a set of results. This is done by examining to what extent results are affected by changes in methods, values of measured and unmeasured variables, and/or assumptions. There are three main purposes of sensitivity analysis. The first one is to evaluate the robustness of research findings. We also use sensitivity analysis when we need to identify critical variables that significantly impact results. And lastly, we use sensitivity analysis to understand the range of certainty or uncertainty in our studies. Results. Joseph Delaney and John Seeger and Tavan and colleagues define and mention multiple instances what may require sensitivity analysis, which are grouped in different dimensions or types of sensitivity analysis. The first dimension is related to the study definitions, and it is about modifying the exposure, outcome, and/or confounders. The second dimension is associated with study design, and it is about changing the data source of population under study. The third dimension alludes to the modeling part of the study. Under each of these dimensions, this lecture will provide some case studies on multiple instances that may require sensitivity analysis, which are listed in the table in your screens. Within the study definition dimension, we have outcome definitions. Outcomes are variables that are monitored during a study to document the impact that a given intervention or exposure has on the health of a given population. In health research and epidemiology, how we define the outcome can significantly influence our interpretation of the data. For example, we might define an outcome using a single diagnosis code, multiple codes, or a combination of diagnoses and procedure codes. Each method may vary in how well it truly reflects the condition we are studying. So the role of sensitivity analysis basically is to promote repeating the analysis with varied definitions, and therefore to assess the robustness of the original definition. And this can result in potential insights into the adequacy of outcome definitions, the credibility enhancement of observed associations through replication of findings, for example, from clinical trials, and it can also result in realizing different lag periods and understanding of the time dimension in outcomes like cancer, where effects may not be immediate. In this slide, we have two studies that use strokes as outcome. Our first study by Cotton and colleagues, published in the Journal of the American Medical Association, JAMA, in 2014, used a single diagnosis code from hospital records to define a stroke. In contrast, the second study we are looking at was carried out by Howard and colleagues, published in Hypertension in 2011. They used multiple diagnosis codes and included imaging results. This broader definition of how to diagnose a stroke captures not only confirmed strokes, but also those diagnosed through imaging techniques, potentially identifying more cases that might be missing when relying solely on diagnosis code, as in the case of Cotton and colleagues in 2014. Within the study definition dimension of sensitivity analysis, we have exposure of covariate definitions. An exposure or a covariate is any factor that may be associated with an outcome of interest. And defining the right exposure window is very important in studies for example, that investigate the effects of substances or interventions over time. And the key challenge here is selecting a time window that captures the exposure during the analysis of the cause or causes of disease, which is what is known as periods that are etiologically relevant. This means we must often make decisions in the middle of uncertainty. So consider the definition of a drug exposure. We would have uncertainty about the most appropriate way to define an exposure window. We could look at daily or monthly exposure, or even cumulatively or within different time windows. But when we alter these definitions, we often see substantially different associations between exposure and outcome. So this is where sensitivity analysis becomes invaluable, because by systematically varying the exposure definition and reanalyzing the data, we could deepen our understanding of the underlying health processes, leading to better and more informed health interventions. Within the study definition dimension of sensitivity analysis, Delaney and Seeger alludes to unmeasured confounding. And within health research, we often operate under the belief that there is no unmeasured confounding in our studies. And this is not a minor detail, because without accounting for all the confounders, our study conclusions may be biased. Unmeasured confounding can be a known variable, which can be absent from our data set. And one example is how obesity is often not included in prescription claims databases. Or it can be an unknown factor which we haven't considered in our study. The presence of these unmeasured variables can significantly alter one's study conclusion. So we should quantify the effects of unmeasured variables. And this exercise helps us to gain a critical understanding of our study's vulnerability, and this assessment also highlights the sensitivity of our results. There are some options in terms of sensitivity analysis in this case, such as eValue, probabilistic bias analysis, simulation studies, or the use of the rule-out approach. In this table, you can see the definitions of these options and the references where you can look at them in more depth. Within health research, it is important to choose suitable treatment and comparison groups to address study limitations. It's not just about what we are studying, but against what benchmark we are measuring it. Let's consider survivorship bias. Survivorship bias is a common problem in experimental design. If we study research like the large-scale longitudinal study published in 2021 by Seltzer and colleagues, who examined the effects of the coronavirus pandemic in the UK, we can analyze the bias due to this survivorship. The study of Seltzer noted that the higher levels of anxiety and depression among surveyed UK residents that occurred during the initial month of the pandemic-related quarantines appeared to decline when those people were survived again in subsequent months. The results of the completed study appeared to show that symptoms of anxiety and depression had fallen among UK residents as the pandemic continued. However, researchers noted that some 40% of people who took the first survey didn't complete follow-up surveys. It was shown later that respondents who were experiencing symptoms of anxiety and depression at the time were less likely to complete subsequent surveys. So datasets of later surveys were made up of a greater share of respondents who were experiencing fewer or no symptoms of depression. An option to reduce the survivorship bias is to compare new interviewees in the case of the mental health survey and prevalent interviewees. New people in the case of our example who have helped to eliminate the survivorship bias. However, be careful to go to another extreme, because focusing only on new people in a cohort has its own drawbacks. It can overlook risk arising over prolonged effects. So the recommendation is to use different comparison groups to assess potential biases. In our example, a solution could have been to interview people in previous waves of the mental health survey, new people in UK, and even new people in other countries. Up to now, we have emphasized the study definition dimension, but Joseph Delaney and John Seeger in 2013 suggested to consider sensitivity analysis for additional aspects related to the study design, specifically to secondary data sources. Secondary data are those that are not usually collected with research objectives in mind, leading to potential selection bias. So here the role of sensitivity analysis is to assess consistency in associations by exploring multiple data sources. For example, let's consider the Medicare data compared to the general practice research database in the US. While Medicare data may offer detailed hospitalization records, it historically lacked routine lab test results, which is a gap that could skew study results. On the other hand, the general practice research database has rich entries on routine medical visits but may not provide as comprehensive hospitalization data as Medicare data in the US. In this comparison, we could take the previous datasets and assess how selection bias and different operational definition of outcomes affect our research results, as well as the existence of measurement error and data misclassification risks. Within the study definition dimension, we have selection bias, which occurs when there is a systematic difference in the inclusion of participants in a study, which may distort the true effect of the exposure and their analysis. And this can arise from either oversampling or undersampling cases exposed to a specific condition or treatment. And the role of sensitivity analysis here is to help to assess how results might change under different assumptions. In clinical trials, for example, several steps can be taken to prevent selection bias, especially at the study design phase, in order not to rely only on post-hoc analysis. Furthermore, Armijo Olivo recommends to randomize procedures to prevent selection bias, and when randomization cannot be possible, one can include all participants as per their original groups, regardless of treatment adherence, to maintain baseline equivalence. In February 2023, Lewis and colleagues published a paper presenting findings from a study exploring the presence and impact of selection bias in observational research related to COVID infection and prognosis. Using data from the Avon Longitudinal Study of Parents and Children, or ALSPAC, along with the UK Biobank, Lewis and colleagues examined how a variety of characteristics influence the likelihood of individuals being included in COVID analytic subsamples. In the plot of your screens, you have the assumed effects of BMI and COVID infection. As you can see, the distributions of the log odds of COVID in selected individuals and all population in the simulations differ widely. The biases of each population versus everyone else outcomes differs, and it can be positive or negative depending on who is selected. Within the study design dimension, we also can look at the cohort definition that we are using. So a cohort comprises a group of people with defined characteristics who are followed up to determine incidence of or mortality from some specific disease, all causes of death, or some other outcome. In the context of the development of therapies, when they enter the trial phase, we often test them on an ideal population, which is composed by those without any complication and likely to adhere to treatment. To ensure that our effect estimates are robust across a wider population, it is imperative to consider multiple cohort definitions and statistical approaches. This not only validates the stability of our findings, but also sheds light on potential effect measure modifications. Different cohorts definitions can affect estimates, for example, by introducing immortal time bias. This has been highlighted for a long time ago. Even in 1997, Sami Suisa and colleagues demonstrated that effect estimates could vary significantly with different cohort definitions, ranging from a hazard ratio of 0.91 to 1.13. This variability underscores the importance of using various assumptions to refine our understanding of the associations we study. So here the role of sensitivity analysis is to assess the impact of different cohort definitions to understand the biases of those definitions in our results. As part of sensitivity analysis, we also need to examine how changes in analytical methods can affect study results. Let's consider the study by Newis, published in 2006, which evaluated the effectiveness of aminocapproic acid compared with apratonin in reducing mortality during coronary artery bypass grafting, or CABG. The researchers used three different analytical methods: traditional regression, propensity score analysis, and physician preference instrumental variable analysis. All three methods consistently showed an increased risk of death associated with apratonin, with relative risk ranging from 1.32 to 1.64. This consistency across diverse methodologies strengthens our confidence in the robustness of these findings. In the statistical modeling dimension, we have the covariate distribution matter, and a covariate distribution is a function that shows all the possible values of an exposure and how often they occur. Covariate transformation implies modifying covariates to better capture the relationship with the outcome. And the advantages of those transformations is that they may capture more accurately the relationship between covariates and outcomes, and also it can reduce the skewness of the covariates, and therefore they improve statistical inferences. The disadvantages of transformations is that they may cause loss of information, especially in the case of the transformation of categorical variables, in which you could group specific categories. And an additional disadvantage of transformation is that the selection of the transformation requires understanding of the distribution of the covariate. So the role of the sensitivity analysis in this case is to test several transformations to compare effects on model outcomes, and to choose good points or transformations with meaningful interpretation in the context of the study. Within the statistical modeling dimension of any sensitivity analysis, a critical aspect that impacts the reliability and validity of our results is related to managing outliers. An outlier is an observation that deviates so much from other observations, which can dramatically skew our results, leading to potentially misleading conclusions, for example, in treatment effects or associations between variables. A known example of the effects of outliers can be seen in the study of Seth and colleagues in 2011 relating to a depression treatment study. The authors carried out a primary analysis following the intention to treat principle found no significant differences in depression reduction between a nurse-led cognitive self-help intervention and standard care among 218 angina patients over 6 months. Sensitivity analysis that excluded patients with high baseline depression levels revealed a significant reduction in depression within the intervention group, suggesting that the initial findings were influenced by these outliers. Identifying outliers is one of the first aspects you need to analyze. We often use visual tools like box plots, which help in quickly spotting these data points as they fall outside the typical range. Additionally, we can employ statistical measures such as set scores, where observations lie more than 3 standard deviations from the mean, and generally consider outliers. Once outliers have been identified, the management of outliers involves some sensitivity analysis. This means analyzing our data with and without these outliers to assess the impact of our conclusions. Such an approach helps in deciding whether outliers should be excluded or adjusted for in the final analysis. The decision to manage outliers is not trivial. It requires careful consideration of the nature of the data and the potential impact on study outcomes. Another aspect within sensitivity analysis is to understand the impact of missing data. Missing data occur when no data value is stored for a variable in an observation. This can be produced by no response in surveys, dropout in clinical trials, incomplete data entries in registers, loss of follow-up, etc. So within a longitudinal health survey, we see a lot of dropouts. So if a study tracks health outcomes over time, sicker or busier individuals might be more likely to drop out of the study. This creates missingness, which is related to the unobserved outcome, health status, which is likely worse among those who drop out. And the implications is that if missing data is not properly addressed, this could lead to biased results, underestimating the health risk or overestimating the treatment effects. So the role of sensitivity analysis here is to assess the robustness and consistency of results by comparing them with different strategies to handle missingness. Here we are going to see the impact of missing data specifically in the study carried out by Gabrielle Kingsley and colleagues in 2012, cited by Tavan and others in 2013. And in this case, Gabrielle describes a trial designed to evaluate the efficacy of methotrexate, a common treatment for psoriatic arthritis. The researchers employed two distinct methods to analyze the data, but basically they focus on intention to treat analysis. But as usual, they had some missing data in their data sets. And to deal with the missing data, they used two techniques, multiple imputation and complete case analysis. The main finding from this analysis diverged enormously. The complete case analysis showed a borderline improvement in the primary outcome, suggesting some benefit of methotrexate. However, the multiple imputed estimates showed no significant improvement. Until now, we have seen different case studies across the study definition dimensions, study design dimension, and statistical model dimension. Now we are going to see or to talk about broader questions related to sensitivity analysis. Tavan and colleagues answered some of the most common questions about sensitivity analysis in their paper in 2013. One of the first questions is about when one should perform sensitivity analysis. Sensitivity analysis should be a standard component of any research to evaluate the robustness of the primary findings. Since all statistical methods used in research are based on assumptions, it's crucial to test these assumptions and assess their impact through sensitivity analysis. Another question is, how many factors can one vary in performing sensitivity analysis? Ideally, sensitivity analysis can assess the impact of key elements either through a factorial design to evaluate individual and combined effects, or by varying one factor at a time. Another question is whether one can perform sensitivity analysis post hoc. It is advisable to document all planned and potential sensitivity analysis in the study's protocol and statistical analysis plan beforehand, although additional analysis may also be required and justified post hoc as unforeseen challenges arise. Another question is how many sensitivity analyses one can perform for a single primary analysis. The key factor in determining the scope and number of sensitivity analyses in a study is not the quantity but the rationale and understanding of the data's nature, where typically focusing on the primary outcome is advised, as conducting multiple analyses on all outcomes is usually impractical and unnecessary. So how does one choose between the results of different sensitivity analyses? The goal of sensitivity analysis is to evaluate the robustness and consistency of study results under various conditions, not to select the best result or alter the primary conclusion, but to validate the confidence and the primary findings and identify other areas for future research if inconsistencies arise. When doing sensitivity analysis, the question often arises, do we need to report all results of the sensitivity analysis? The answer is yes, particularly when the results deviate from or contradict the primary outcomes of our study. Such difference can provide invaluable insights into the limitations and applicability of our findings. It is essential to document these discrepancies as they can lead to a deeper understanding and potentially guide future research directions. However, if the sensitivity analysis confirms that our results are robust, that is, they remain unchanged across different scenarios, a brief statement may suffice. This serves to reassure readers of the reliability of our findings without overloading them with redundant information. When it comes to presenting this analysis, the method of reporting can vary based on the complexity and number of scenarios tested. For simpler or fewer scenarios, summarizing the results in the text of the paper often is enough. However, for more complex or numerous scenarios, tabular or graphical presentations can provide clearer insights. For example, using tables allows readers to precisely see how varying assumptions influence the reported association. This is particularly useful for direct comparisons across different subpopulations or assumptions. On the other hand, graphical presentations are invaluable when dealing with continuous variables or when illustrating the impact of potential confounders. Sensitivity analyses are more than just statistical procedures. They are an important stage within the research process that allow us to validate the robustness and credibility of research findings. Robust results across various scenarios and assumptions enhance the trustworthiness of one's study conclusions. So sensitivity analysis should be included within the planning and development of health studies, which should be evident in the final research document, which should comprehensively document all conducted sensitivity analysis, along with the rationale and the implications of the findings. These are the references of this lecture. Thanks for listening.
Thank you for watching. For more information, visit our website www.radiance.org.uk.